So in this video, we're going to talk about these two words, accuracy, precision, and then also cover percent error. So this is basically going to be all of page 11. And actually, the word accuracy happens to be back on page 10 because of that weird snafu we had with those equations on page 10, not taking up as much space as they should have. But I would highly recommend that you not write any of this stuff over there on page 10. Let's keep it all together on page 11 so we don't have to go searching for definitions or the differences between these words. So go ahead and write accuracy at the top of the page and then leave a little bit of space because we're going to write a little bit more in between these definitions here. So accuracy and precision. Oftentimes we want to be both, but that doesn't mean that they're the same thing. These are two different terms, two different measures of how good we are in the lab and outside of the lab as well. Accuracy is all about how close the measured value is to the actual value, how good my measurement is, how close it is to the goal. And to help remember this, sometimes I like to think of accurate as accurate, because it's all about whether or not that measurement or that attempt that I made being right or close to what it should be. Precision, on the other hand, isn't about being right or wrong. It's just about how close a set or a series of measurements are to one another. So they can be completely off the mark, nowhere close to our goal, but as long as our separate measurements are close together, then they can be precise. Another word for precise is reproducible. We can do the same thing over and over and over again, and we get the same or at least similar results. And that precision is very important for scientists in general because things might not always turn out right, but you need to do them in a way that they will turn out the same over and over again. And it's going to minimize that systemic error. Now, we are going to be reflecting on things and measurements in the lab being accurate and precise. So we need to add a little bit more detail here to these definitions. In the lab, in order to tell if something is accurate, we're going to take the average of all of our values, all of the measurements that we make for a single kind of trial, and compare that average to the true value. And the closer that average is to the true value, the more accurate it's going to be. Now, I do say find the average of them to compare, because in science we do tend to take 1, 2, 3, 4, and 3 or 4 generally measurements and put them all together to help minimize the amount of error we might have with a single measurement. But even if we don't take repeat measurements, we can compare a single data point to the true value to see if that single data point is accurate. But most of the time we'll be averaging sets of values. And if you don't remember, in order to find an average, we would have to add all of the values up for a given set of trials, add them together, and then divide by the number of values. So if we have 3 separate trials for a single measurement, we add all 3 of those numbers together, then we divide by 3. If there were 5 numbers, we add all 5 together, then we divide by 5. And that's going to get us our average. Make a note of it if that's not something that you necessarily remember off the top of your head, but if averages are the easiest thing ever, you might not need to add that little side note. Now, precision in the lab. If we're measuring how close or far apart numbers are from each other, we're not going to be looking at averages. We're going to be looking at the range of those values. And that range, how far apart they are, we want them to be close together to be precise. So we want a smaller range to indicate that we have a more precise measurement. Bigger ranges means less precise. And in case you forgot, if we are trying to find the range of a set of values, we're really just going to have to take the biggest value, whichever one is the largest out of that set, out of that those trials or values, and subtract the smallest from it. So biggest minus smallest will get us our range. Now you see below on the page that we do have a set of data points that we are going to look at with the averages, and But let's go ahead and look at some simpler versions of accuracy and precision that don't have any numbers first, just to make sure that we understand the ideas in general. So I'm going to look at each of these targets and the darts, really, that were thrown at each of these targets and ask myself, were they accurate, precise, both, or neither? So I'm just going to put an A and a P next to each of these so that I can either cross it out or give it a check mark depending on each. This first dartboard, our darts are scattered all around and none of them are anywhere close to the middle. And so that is not accurate because we don't have any darts that are approaching the middle, approaching the goal. And this is also not precise because we don't have any darts that are really close together, not consistent in the way that they're throwing these darts. That second example, also not accurate because once again, we don't have any darts anywhere close to the goal, close to the center. But these darts are precise because at the very least they are close together. And then of course this last example, we are accurate because all of those darts are hitting the center, and because they're all close together still and at the center, that means that we are also precise. So hopefully that helps you visualize things a little bit more. We're not really going to be throwing darts around the chemistry classroom though. So instead, let's look at this data table of values. Here I've already found the average and the range for you so that we can really just focus on interpreting and understanding these numbers and how we can use them to reflect on the accuracy and precision of these three anonymous students. Whenever I ask you to talk about the accuracy and precision of different sets of data, I always want you to make sure to mention who was the most accurate and who was the least accurate, who was the most precise and who was the least precise. And sometimes we're going to have a tie or things are going to be really, really close, but those are the things I need you to be looking for and reflecting on. So over off to the side in this right-hand side, go ahead and write down student A, B, and C. As we figure out who is most and least accurate and precise, we'll make those notes off to the side there. So if we start by looking for who was the most accurate, like we just said up above, accuracy comes by looking at the averages and comparing which one and finding which one is closest to the true or accepted value. And up here at the top of above the table tells us the true value is 10, and the student who is closest to 10 is student C. So we can say that student C is the most accurate. The least accurate person is the person who's farthest away from our true value. So we might need to do a little bit of math here, either in our head or in our calculator. I can see with this value that I'm 0.13 away from 10. But here, if we do 10 minus 9.79, my calculator will tell me that I'm 0.21 off. So I just did a little bit of subtraction just to help put a number to how close or far away I am, because it seemed kind of similar, but now I can tell that the student who is farthest from our accurate, true mass is student B, and that means that they were the least accurate measurer. Hopefully that's not too bad so far, just looking at these numbers. Now if we're looking for most and least precise, then our most precise, if you remember, precision comes back to range, and more precision has a smaller range. So the smallest range that we have is student C. So student C also happens to be the most precise. The least precise person is going to be the one that has the largest range, and that is definitely going to belong to student A. So biggest range means they are the least precise. And this is exactly what I want you to do on page 12 with the data table that you have given to you there, You're going to have to find the averages and the ranges for yourself. Let me go ahead and pull that up here. So we've got these data points for you, but I want to see you practice finding the average and the range. So find Lisa's average and range, Lamont and Lee's average and range, and maybe write those numbers down here, kind of like I did below my table, so you can keep them nice and organized. And then in this space down below, you can start reflecting on who was the most accurate and who was least accurate, most precise and least precise. And my hint for you is that there will be a tie for one of those titles. And so you can say these guys were tied for most this, or tied for least that. So do your best on those problems. Let me know if you get stuck or if you're having trouble with any of that calculation stuff, and I would love to help you out, but I hope that you can take care of those averages and ranges on your own. While you're at it, I know I was pointing out that question number 2, that's exactly what we did, but go ahead and take care of question number 1 on this page as well. It's a quick little qualitative, quantitative, shouldn't take you very long, but I want to make sure to recap some of those old topics we haven't talked about for a while. Work on that, maybe pause this video and come back to it, because we're going to move on to percent error. So the bottom of page 11 is where we get to write down our percent error definition and formula. And percent error is going to be important for us when we're trying to reflect on the accuracy of a measurement, because just looking at how far off, doing that subtraction like what I did in the last problem, tells me how far I am from the value I'm supposed to be, but it doesn't really give me an idea of how good or bad that distance from the correct answer is. So just to kind of give you an idea, if I tell you that I made a measurement and I was 5 off on that measurement, you think that's a good measurement or not? A lot of people in class were like, it's kind of a big amount off. Most of the distances from the accepted value we were seeing was like less than 1. So a lot of people told me like, maybe you should try harder. But then I told them, what if I was counting beads and I was only 5 off when I was counting 10,000 beads? And people's eyes lit up. They're like, oh yeah, well, 5 off then, that's a lot better than I thought. But if I was counting only like 10 beads and I was 5 off, and once again, people are giving me this look like, how could you possibly be that far off? The size of what I'm trying to count or measure matters when we talk about how accurate we are, how good our measurement is. And that's what this percent error formula does for us. We've got our E, which is our experimental value, our best attempt in the lab to get an answer, but it might not be perfect. And then we have the accepted or true value, which is our A. And so this percent error formula starts on top in these parentheses by having you subtract E minus A. We're finding the difference between what I got and what I should have gotten. Like when I was saying, I'm 5 off. But that's not the end of the story. What we do next is really important. So we divide by that accepted measurement size. So the larger that A is, the larger that number I should have gotten is, the smaller my error is, because we're dividing by a big number that gives us a smaller answer. So that means smaller error. If I have a small A value, dividing by a smaller number is going to give us a larger error value. So this percent error formula just kind of puts that error, how off I am from my answer, into context to turn it into a percent, almost like grading your attempt, your measurement at how good that is. Now, one thing to remember with this equation is order of operations, PEMDAS. Parentheses have to be the first thing that happens in this calculation. So you're either going to have to physically write those parentheses in your calculator if you're trying to put all the numbers in this equation in your calculator at once, or you're going to have to do this in 2 steps and manually do that subtraction first, push enter, find that answer, and then do that divided by and times that 100. So you have to make sure that that happens first, or else your answer, your calculation is going to be off. So either use the parentheses or follow the rules of those order of operations and do the parentheses first before you follow through with the rest of the calculation. So let's go ahead and do a couple examples, because plugging numbers into the equation is actually the easy part of this. The calculator is going to do most of the work for us. What we need to take charge of and be sure of is which of the numbers in our problem, because there's going to be two, which one is our E and which one is our A. Remember, E stands for experimental, and that's the one I like to look for. I keep asking myself, did a student measure this? Did they try on this, or were they told to do this? Because if they were told to get this, or they said that they should have gotten this, that should have, could have, is the accepted value. But if it says a student measured this, or they got this, then that means that they had their hands on something, they were trying their best, but maybe it didn't turn out perfect. And that's going to be the value that we find as our E. So as we read through this first problem, pay attention and try and pick out which of these two numbers did the student physically have their hands on doing their best when they got that result. So this first example says that there are 34 questions on a test, and John only answers 22 of them correctly. What is the percent error? So, which of these numbers did the student take charge of and actually, or experimentally, I suppose, would be the right way to put it, experimentally attempt on this test? Hopefully you're saying and thinking that 22. John answered 22 of them. Did a student do this? Did a student measure this? Yes, they did. So that is our E. Notice it just said there are 34 questions on a test, not that he got 34 questions. It's nothing about the student there. It's all about the test, the expectation there. And so that is going to be our accepted value. Then coming back to our equation was E minus A. So that's going to be 22 minus 34 in parentheses. Divided by A means dividing by 34. And of course the times 100 part. This is the absolute minimum that I have to see in order to support your answer. I cannot just see an answer on the page. I know you're doing your work in your calculator. I'm hoping and begging you to use a calculator. You don't have to do all the math in your head, but I do need to see your plan for what you're putting in your calculator on your page. It's the only way I can see. Maybe you flipped these up. Maybe you have the wrong number on the bottom. It's the only way it can help you if you're struggling or getting it wrong, is if I see that work. So I'm going to do this in a couple of steps just to help make it extra visible, but I don't need to see this intermediate green step here. If I start by doing 22 minus 34, yes, that is going to be a negative number, negative 12 to be exact, and that negative just tells us that he was below where he should have been. And that makes sense. On a test, normally, if you're making errors, your grade is going to be lower than a 100. But in chemistry, we can be off. We can have error in our measurements and in our answers that maybe are too big for what's expected. Maybe we had some contamination in the lab, or we didn't finish the reaction that was breaking down our compound. We might be left with more than we should have. And even if we have more, that's not like bonus points on a test. We're still off. We still have error. It just might be a positive error where we went over what we should have gotten instead of a negative error where we were below what we should have gotten. So if the negatives throw you off, you can kind of leave them off to the side. They're not going to be the biggest deal here, but they will be a part of our calculation, and they do give us some information here. So I did my subtraction first. Now I can feel free to do all the rest of this division and multiplication. And we get negative 35.29. And there are some other numbers, but we're actually not going to need to keep even this many numbers, because if you remember our conversation and notes about significant figures, is we only need to keep as many digits in our answer, we only need to keep as many sig figs in our answer as our original measurements. And each of these numbers we were given only had 2 significant figures, so I only want to keep the first 2 digits in my answer. So the full correct answer here would be 35% error. Negative 35 if we want to be exact there. Hopefully that's not too bad, just making our answer round to match our original numbers. Now, this next problem I'm not actually going to do the whole thing on. I'm just going to get you started, make sure we find our E and our A. As we're reading it, it says the label says the rope is 2.15 feet long. That's not what a student did. That's what it says it should have. The label says it's that long. So that's going to be our accepted measurement. John measures the rope as 1.85 feet. Okay, did a student do that? Did a student measure it? Yes. So that's the experimental attempt. So make sure you show your work, at the very least what I showed here in red, and then our final answer here at the end. I don't need to see the other green stuff in between if you don't want to, but I do need to see at least the original setup and that final fully rounded answer. And I will tell you that this answer is going to be about 14, but pay attention to your sig figs here. I should have 3 significant figures in our final answer, not just 2. So don't just write 14 as your answer. And it's going to be a little bit more to that number. Let me know if you're not getting something that's about 14, and I'll help you fix that up and figure it out. And then go on and work a couple of problems on page 13. That's where the percent error practice problems are, and you don't have to do question 10. So I believe it's just 7, 8, and 9 down there below all of the other significant figures practice that we have there. So work on that. We should be able to finish all of our packet all the way up through page 13 now. So make sure that you're taking care of that. Keeping up to date with anything that you haven't gotten done in the past.